July 29, 2025, 23:24:50 UTC. An earthquake off Kamchatka shattered seismic records, magnitude 8.8, more than 600 kilometers ruptured, unleashing more than 1 billion joules into the earth. But what truly stunned scientists was not the quake's size, it was the chain reaction that followed: volcanoes awakening, ocean floors uplifting, and an energy pulse echoing around the globe. Why is the aftermath still spreading, and what new force did this event awaken beneath our feet? Catalog records pinpoint the epicenter of the July 29, 2025 earthquake at 23:24:50 UTC, just off the eastern coast of Kamchatka. The rupture began without warning, tearing through more than 600 kilometers of the subduction zone in less than 5 minutes. Instrumental readings confirmed a moment magnitude 8.8, placing this event among the handful of largest earthquakes ever measured. Finite fault analyses from USGS and JPL revealed maximum slip values between 31 and 40 meters, concentrated at depths of 8 to 25 kilometers. The scale of movement dwarfed most previous events. Only the 1960 Chile, 1964, Alaska, 2011, Tohoku, and 2004 Sumatra earthquakes exceeded it in magnitude. The rupture propagated southwest at speeds of up to 3.5 kilometers per second, releasing more than 1 trillion joules into the crust. Within seconds, seismic stations around the globe captured the initial P&S wave arrivals, while ground-based GNSS receivers and satellite radar tracked the surface shifting by meters over wide areas. Early INSAR results from Sentinel-1 and ALOS-2 satellites showed a broad zone of uplift and subsidence, with the sharpest deformation landward of the main slip patch. These measurements, released only hours after the quake, revealed a pattern of displacement that stunned even seasoned catalog analysts. The ground had shifted as much as 7 meters in the line of sight, with some coastal segments permanently offset by over 4 meters. Catalog duty officers noted the event's rupture length and slip values as outliers, flagging the main shock for immediate global review. The event was quickly assigned a unique identifier in seismic bulletins, and a dedicated map was published, tracing the rupture from its nucleation point to the farthest aftershock clusters. The precision of these early metrics set the stage for a deeper investigation into what made this earthquake and its aftermath so extraordinary. Seismic stations from Anchorage to Canberra recorded the first P waves from the Kamchatka rupture within minutes of the origin time. On raw iris network traces, the initial compressional pulse arrives as a sharp, impulsive spike, followed by the slower, rolling S wave. At global distances, the separation between these wave types is unmistakable. P waves racing ahead at nearly 8 kilometers per second, S waves trailing at about half that speed. Analysts picking these arrivals noted the extraordinary clarity and amplitude, with even distant stations in Africa and South America logging high signal-to-noise ratios. The rupture itself lasted between 180 seconds and 270 seconds, a duration confirmed by back projection studies and finite fault modeling. This extended slip sequence produced a seismic signature that spanned the entire globe, lighting up the global network in a near-simultaneous chorus. On the iris waveform displays, the propagation is visible as a rolling front, with P and S arrivals stacking up across continents. The event's long duration and massive energy release allowed surface waves to wrap around the planet multiple times, producing sustained oscillations that lingered for hours. Sample seismograms from IRIS stations such as ANMO in New Mexico, BFO in Germany, and MAJO in Japan show the rupture's fingerprint: a prominent P-wave onset, a broad S-wave peak, and a complex multi-lobed surface wave train. The amplitude and timing of these signals enabled rapid triangulation of the rupture's extent and speed. Seismologists use these traces to reconstruct the rupture's southwestward sweep, matching model predictions with real-time observations. The global detectability of this event is not just a function of its magnitude, but of its physical propagation. Every major seismic array captured the event in detail, allowing researchers to compare raw traces side by side. The result is a clear record of a planetary-scale disturbance, one whose waveform signatures will be archived and studied for decades to come. The numbers behind the Kamchatka quake defy the imagination. Calculations from the USGS and international seismic teams place the total seismic moment energy release at more than 1 × 10⁸ joules. That is greater than the combined annual energy use of some nations, compressed into less than 5 minutes. On paper, this single event unleashed energy equivalent to over 250 million tons of TNT. For seismologists, the raw power was undeniable, but translating that figure into something tangible required a different kind of reckoning. A handwritten entry in the USGS duty log at 0014 UTC captures the moment. Energy release off scale. Main slip patch exceeds 35 meters. Confirm magnitude, repeat calculations. This is not a drill. The duty officer's note, scribbled in the margin, underlines the urgency. Request satellite confirmation. Surface displacement seems anomalous. Awaiting INSAR. The conversion from seismic moment to joules is straightforward in theory, but the magnitude of this earthquake forced analysts to check, then recheck every parameter. With a moment magnitude of 8.8, the energy calculation follows a standard formula. The log of E equals 1.5 times moment magnitude plus 4.8. Plugging in the numbers, the answer is staggering, more than 1 × 10⁸ joules. The rupture length, the maximum slip, and the depth all pointed to an event that would stand apart in the seismic record. As the data poured in, every major seismic agency flagged the event for global review. The scale of the energy release demanded external verification. Satellite teams at ESA and JPL were alerted within minutes, tasked with mapping the surface shift from orbit. Analysts knew that only independent geodetic measurements could confirm whether the ground had truly moved as much as the seismic model suggested. The request for satellite overpasses became a priority, setting the stage for a new phase of investigation, one that would soon reveal just how far the planet itself had shifted. Sentinel-1's first post-quake pass swept over the Kamchatka coastline less than 36 hours after the rupture, recording a raw radar image that would soon stun the global geodesy community. The European Space Agency Operations Hub, led that night by Juliette Blanc, rerouted the satellite for a targeted synthetic aperture radar acquisition, orbit 51432, descending, timestamp 2025 August 1st at 4:17 UTC. Within hours, the ALO-S2 mission from JAXA on Ascending Track 166 gathered its own high-resolution scene, capturing the deformation zone from a second vantage point. The first interferograms, those rainbow-colored maps of ground motion, arrived in scientists' inboxes before sunrise. Each colored fringe on the map represented a full 2.8 centimeters of line-of-sight displacement. In some places, the fringes were packed so tightly they merged into a blur, indicating the ground had moved so far that the radar signal lost track. Analysts measured a maximum of 7.2 meters of displacement in the line of sight, with the largest offsets clustered just inland from the main slip patch. The pattern radiated outward, a broad elliptical zone of uplift surrounded by deep subsidence, with the sharpest gradient running parallel to the coast. Juliette Blanc later described the moment in a team chat. She said the first interferograms left the team stunned. The displacement was off scale. The European Space Agency and JAXA teams flagged phase ambiguities where the radar signal could no longer resolve the true shift, a sign that the quake's surface movement had exceeded the designed measurement range. Metadata for each pass was archived meticulously. Sentinel-1 orbit 51432 and ALO-S2, Track 166 were both referenced to pre-event cycles from July 21st and July 25th. The difference between pre- and post-event images revealed the raw fingerprint of the rupture, undistorted by ground-based assumptions. Across the northern aftershock zone, the interferograms showed complex multi-lobed patterns, evidence of secondary slip patches, and possible shallow faulting. In the southern sector, the displacement field stretched over 400 kilometers, with a subtle twist marking the transition from uplift to subsidence. Analysts traced this outline directly onto satellite maps, overlaying it with seismic catalog rupture models. For the first time, the full extent of the surface shift was visible from space, raw, quantitative, and impossible to ignore. The satellite data, stripped of interpretation, became the new reference for ground truth, setting a benchmark for every subsequent measurement to follow. Ground-based GNSS receivers along the Kamchatka coast registered permanent offsets within minutes of the earthquake. At station KMT, coordinates shifted 3.8 meters north and 1.2 meters upward, while site PTR, over 150 kilometers away, recorded a horizontal jump of nearly 2 meters. These abrupt displacements, logged in the IGS network archive, aligned with the main slip patch modeled from seismic data. Each GNSS station's time series shows a step-like shift at 2325 UTC, with the largest offsets clustering along a northeast to southwest axis parallel to the rupture. To cross-check these land-based measurements, ocean altimetry provided a rare independent window into the quake's offshore impact. Sentinel-3A's SRAL altimeter crossed track 743 above the rupture zone at 2:15 UTC on July 30th, less than 3 hours after the main shock. The processed sea surface height profile revealed a pronounced anomaly, a rise of 21.4 centimeters centered at 54.2 degrees north, 160.5 degrees east, relative to the previous cycle's baseline. Jason CS followed on track 117 at 350 UTC, confirming a 19.7 centimeter deviation near 52.9 degrees north, 162.0 degrees east. Sentinel-3B on track 752 detected an 18.8 centimeter uplift several hours later. These values, referenced to pre-event cycles and corrected for tides, match the spatial pattern of maximum slip inferred from both GNSS and INSAR. The tight correspondence between land and ocean measurements left little room for doubt. GNSS vectors radiated outward from the epicenter, while the altimetry waveforms traced a continuous band of uplift across the trench. In the near field, tide gauges and DART buoys corroborated the satellite readings, with Kamchatka's East Coast gauges registering a sharp stepwise sea level increase of 20 to 22 centimeters. Analysts at JPL and ESA compared these data sets side by side, confirming that the deformation spanned both continents and ocean basins. For the first time, the magnitude of ground and sea displacement could be locked in with sub-centimeter precision using independent methods. The GNSS and altimetry records together established the earthquake's true scale, a multi-meter shift on land echoed by a measurable pulse in the ocean surface. The agreement between these vectors and waveforms became the new benchmark for modeling the stress changes that followed, anchoring every subsequent analysis of aftershocks, volcanic responses, and global deformation patterns. Coulomb stress calculations began within hours of the main shock, as modelers at USGS and JPL worked to map how the rupture altered the balance of forces across the crust. The numbers told a story of both risk and relief, drawn in gradients of positive and negative stress that radiated from a 600-kilometer fault. Where the rupture released strain, broad swaths of crust showed negative lobes, zones where the likelihood of another large earthquake had dropped by up to 2.5 bars. But the concern lay in the positive lobes, where static stress had increased, sometimes by more than half a bar, nudging nearby faults closer to failure. Inputs from INSAR, GNSS, and finite fault models defined the rupture geometry and slip distribution with rare precision. The foreshock sequence, including the magnitude 7.0 and magnitude 7.4 events, had already primed the main shock patch, with previous stress modeling showing a cumulative increase of about 0.5 bars in the nucleation area. Now, after the main event, the static stress field was redrawn. Along the southern margin, stress had jumped by more than half a bar, while the northwest edge slipped into a shadow, suppressing the chance of immediate aftershocks. Analysts mapped these stress changes onto known fault lines, tracing where the risk of further rupture had risen. The southern aftershock zone, already flagged by catalog relocations, fell squarely within a positive lobe. Here, the probability of triggered events was highest, and the pattern matched the early aftershock clusters cataloged by IRIS and USGS. In contrast, the northern segment, sitting in a negative lobe, saw aftershock rates drop off sharply after the first day. The modeling teams published their first results on July 31, 2025, overlaying the stress lobes on seismicity maps and INSAR displacement fields. Their findings were consistent. The static stress change on the main rupture plane ranged from -2.5 to +0.5 bars, with the largest increases focused at the southern and down-dip edges. These figures reflected both the slip distribution and the rupture directivity, with the southwestward propagation concentrating energy into the southern sector. For global hazard assessment, the key was understanding where these stress changes might cascade. The positive lobes traced a path that extended beyond the immediate rupture, touching adjacent segments of the subduction zone and several upper plate faults. Modelers cautioned that these areas, now sitting under increased stress, would require close monitoring in the weeks ahead. The stress field, mapped in bars and color gradients, became the new reference for forecasting aftershock hazard and evaluating the potential for further large events in the region. When the Kamchatka rupture began, it did not just tear a straight line through the crust. Instead, the break raced southwest, carving a jagged path at speeds averaging close to 3 kilometers per second, sometimes even faster. This directionality, known as rupture directivity, focused the earthquake's energy like a spotlight. Areas lying in the path of the rupture's advance faced far stronger shaking and greater permanent displacement than regions equidistant in other directions. Seismic modelers traced this effect using back projection techniques, stacking waveforms from dozens of seismic arrays around the world. The result was a clear time-lapse map showing the rupture front sweeping southwest along the subduction boundary, with energy pulses building in intensity as the break accelerated through the main slip patches. At the surface, this meant that communities and monitoring stations hundreds of kilometers down the rupture recorded ground motions and offsets that seemed outsized for their distance from the epicenter. INSAR and GNSS data revealed that some sites more than 200 kilometers southwest of the epicenter shifted by over 2 meters, an anomaly only fully explained by the focused energy of directivity. Meanwhile, locations off the main rupture path, even if closer to the epicenter, experienced less dramatic effects. The asymmetric pattern of damage and displacement, now visible in both satellite data and field observations, matched the predictions of directivity models to a remarkable degree. Rupture speed played a crucial role. When the fault breaks quickly, seismic waves from different segments pile up, amplifying ground motion in the direction of rupture. For the Kamchatka event, the main slip patches released energy in rapid succession, creating constructive interference that amplified shaking and permanent movement along the rupture's southwest axis. This is not just theory. Modelers at JPL and Caltech generated directivity animations using real-time seismic and satellite inputs, overlaying observed ground shifts with simulated wave fronts. The match was striking. The strongest, most abrupt displacements lined up with the predicted directivity lobes. One modeler described the process in a post-event briefing. They said they watched the rupture front sweep across the fault at nearly 3 kilometers per second. The energy was not radiated evenly, it was aimed, almost like a jet. That is why GNSS sites far down the line saw such huge jumps. The implications go beyond local impacts. Directivity shapes everything from the reach of damaging shaking to the pattern of aftershocks, and even the potential for distant triggering. As the back projection output circulated among research teams, the focus shifted to real-world checks, comparing model predictions with observed ground truth from satellites, GNSS, and ocean altimetry. Each new dataset added another layer of confirmation, linking the mechanics of rupture directivity to the lived experience on the ground and the lasting imprint on the planet's surface. Within hours of the Kamchatka earthquake, the region's volcano observatories began logging a sequence of eruptions and unrest that defied statistical expectation. Across the peninsula, 7 volcanoes either erupted or showed clear signs of new activity within a span of just 4 days. The timeline started with Klyuchevskaya Sopka. Seismic and gas monitoring had already shown above average sulfur dioxide emissions and minor ground uplift in July, but the main eruption began less than 12 hours after the earthquake. VIRs and astrothermal sensors picked up a hotspot at the summit, while local seismometers registered a surge of volcanic tremor. Ash and incandescent material fountained from the crater in a Strombolian Vulcanian-style event. For a volcano that typically erupts every 1 to 3 years, the timing was abrupt, but not entirely outside the realm of possibility. Clustering drew attention. By the next day, Shivaluk and Bazimiani had both produced significant ash plumes. Shivaluk, already in a period of ongoing unrest, sent pyroclastic flows down its flanks within 24 hours of the main shock. Bazimiani followed with an explosive dome collapse 48 hours after the earthquake, sending ash several kilometers into the atmosphere. Karimsky, another frequently active system, renewed its eruption 2 to 3 days after the earthquake, with small ash bursts recorded by infrasound arrays and satellite thermal sensors. Avachinsky, usually quiet for decades at a time, showed minor explosions, though the precise timing and connection to the earthquake remain uncertain. The real anomaly came from Krasheninnikov. This volcano had been dormant for more than 5 centuries, with no recorded eruptions in modern history. Yet on August 3rd, just 4 days after the main shock, an explosive eruption sent a 6-kilometer ash column skyward. Regional experts described Krasheninnikov's outburst as a textbook example of dynamic triggering. There was no measurable unrest beforehand, no satellite thermal anomaly, and a sudden violent awakening immediately following the passage of seismic waves. Mutnovsky, by contrast, showed only hydrothermal changes. Persistent thermal signatures intensified after the quake, but no magmatic eruption occurred. Sulfur dioxide and thermal data from Sentinel-5P and MODIS confirmed abnormal gas and heat output at several volcanoes, with spikes at Klyuchevskaya and Krasheninnikov standing out against baseline values. A summary table published by the Kamchatka branch of the Russian Academy of Sciences documented eruption onsets, gas flux, and thermal anomalies for each volcano, cross-referenced with seismic wave arrival times. The probability of so many volcanoes erupting in such a tight window without a common trigger was calculated at less than 1 in 1,000 for the region's typical background rates. A volcanologist with decades of experience in Kamchatka put it this way: "They said we have seen clusters before, but never with this timing, and never with a volcano like Krasheninnikov, silent for centuries, suddenly erupting days after a megathrust event. The odds are vanishingly small without some external nudge." Thermal and sulfur dioxide data, eruption intervals, and expert assessment all pointed to a mix of dynamic triggering and accelerated unrest. For the frequently active volcanoes, the earthquake likely nudged systems already close to eruption. For Krasheninnikov, the event crossed a threshold, releasing gas and pressure that had built up over generations. The synchronized timeline of these eruptions provided a rare natural experiment, one that would fuel debate about the true reach of a megaquake's power and the fragile balance beneath the Earth's surface. At 2:43 UTC, the research vessel Atlantis logged a moment that would ripple through the scientific community. The Jason ROV, deployed just hours after the main shock, transmitted live images from the seafloor above the rupture zone. What appeared at first as a jagged crack soon revealed itself as a fresh fissure stretching for hundreds of meters along the sedimented slope. The walls of the fissure glistened in the lights, and a faint shimmer, possibly hydrothermal or magmatic in origin, rose from its depths. Dive leader Dan Fornari later recorded in the dive logs that the note read, "Glowing fissure 243 UTC, location matches predicted slip patch, rerouting survey grid." The Atlantis team had arrived with a pre-quake multi-beam bathymetry survey, completed just 2 months earlier. Now, with the ROV sonar and high-resolution cameras, they mapped the same stretch of seabed, grid by grid. The difference was unmistakable. In the area above the principal rupture, the seafloor had lifted by nearly 2 meters. The multi-beam data, processed on board and cross-checked against the earlier survey, showed a broad dome of uplift flanked by subsidence troughs to the north and to the south. The uplift's magnitude and shape matched predictions from finite fault models, but the precision of the bathymetry left little doubt. The crust had been wrenched upward in a single catastrophic motion. Further along the fissure, the ROV encountered plumes of cloudy water and scattered patches of newly exposed rock. Temperature probes recorded a subtle but persistent rise, evidence that fluids heated by the sudden fracturing were now venting through the fresh cracks. The team collected water and sediment samples, hoping to trace any chemical signatures that might point to magmatic intrusion or rapid hydrothermal circulation. In the dive summary, Fornari noted anomalous venting, temperature gradient across fissure, possible methane bubbles observed. The bathymetric comparison became the centerpiece of the Atlantis cruise report. Overlaying pre- and post-quake grids, the scientists traced the uplift axis directly over the main slip patch mapped by interferometric synthetic aperture radar and by global navigation satellite system measurements. The vertical displacement measured at 1.8 to 2.1 meters over a swath nearly 400 meters wide, and it was consistent with the earthquake's modeled slip and with the observed tsunami amplitude. These findings were relayed to shore in near real time, prompting immediate requests for further ROV dives and additional multi-beam passes. The visual evidence from the seafloor brought a new dimension to the unfolding investigation. For years, scientists had inferred such changes from satellite data and from indirect measurements. Now, for the first time in this region, they could point to direct physical proof: a fresh fissure, a measurable uplift, and a seafloor transformed by the raw force of the planet's shifting plates. The Atlantis logs, the ROV footage, and the bathymetric grids would become reference points for every subsequent study of the Kamchatka earthquake's offshore impact. At 6:12 UTC on July 30th, a new set of data arrived at the Berkeley Seismological Laboratory. The team, led by Barbara Romanovich, was already combing through global seismic records when a stack of spectrograms caught their attention. These displays, built from hundreds of broadband stations across the IRIS and GSN networks, revealed something unexpected: a low-frequency signal, persistent and unusually intense, lingering well after the main shock surface waves had faded. The amplitude in the 0.3 to 2 MHz band was elevated for days, outlasting even the strongest aftershocks. This was not just the classic ringing seen after Tohoku or Sumatra. The decay rate was slower, the energy more broadly distributed across modes, and the spectral lines showed subtle shifts not present in the reference stacks from previous megaquakes. A handwritten note in the lab's notebook from that morning reads, "Stacked modes, prolonged high amplitude, not Tohoku, not Chile. Check instrument response and filter settings. Rerun with alternate stations." The team reran the analysis, swapping out noisy stations and adjusting filters. The anomaly persisted. Romanovich's group compared the Kamchatka spectrograms to those from 2011 and 2004, normalizing for magnitude and instrument upgrades. The difference remained. The planet's low-frequency oscillations triggered by the 8.8 rupture simply refused to fade on schedule. By noon, the lab's Slack channel was buzzing with debate. Some suspected instrument drift or a global network artifact. Others pointed to the earthquake's unusual rupture geometry and slip concentration as possible causes. Romanovich, cautious but intrigued, typed that it is rare to detect this kind of low-frequency anomaly, but the physics do not immediately demand a new planetary paradigm. The prolonged ringing, now confirmed across continents, raised questions that would ripple through the geophysical community. Was this a sign of deeper coupling within the Earth's core and mantle, or simply the most sensitive detection yet of a known phenomenon? The lab's notebook, with its raw timestamp and skepticism, captured the scientific mood, a blend of excitement, rigor, and unease in the face of an unexplained echo from the planet's depths. Tsunami models issued in the first hour after the Kamchatka rupture projected wave heights across the Pacific, with impact zones stretching from the Russian Far East to the shores of Alaska and northern Japan. Within 6 hours, hazard bulletins listed more than a dozen coastal regions under active watch, each flagged for possible inundation or dangerous currents. In Huatulco, Mexico, harbor logs recorded an abrupt sea withdrawal, followed by a surge that swept fishing boats inland, evidence of the quake's reach far beyond its epicenter. Tide gauges in Hawaii and California registered stepwise sea level changes, confirming that the energy unleashed off Kamchatka had traveled thousands of kilometers, reshaping coastlines and disrupting marine traffic. The Pacific Tsunami Warning Center's real-time dashboard logged 120 distinct alerts and advisories within the first 12 hours. Some communities evacuated in darkness, guided only by sirens and radio updates. In Kamchatka itself, emergency crews worked through the night, documenting landslides, collapsed roads, and isolated villages. Power outages and damaged infrastructure complicated rescue efforts, while aftershocks rattled nerves and hampered recovery. Scientists tracking the event assembled a watch list of regions where stress changes and ground deformation might trigger further hazards. The list included not only aftershock zones, but also volcanic systems and offshore faults now sitting under heightened scrutiny. Hazard assessment teams published daily updates, mapping the evolving risk landscape as new data arrived from satellites and field stations. Each entry in the hazard log, a new aftershock, a spike in volcanic gas, a report of ground cracking added to the uncertainty, reminding everyone that the full consequences of the quake were still unfolding. In the midst of this, a deeper question lingered. Could the observed synchrony in volcanic unrest, seafloor fissures, and distant tremors be explained by known geophysical processes? Or was something more complex at play? As researchers parsed the latest readings, the boundaries between coincidence and causation blurred. The event had exposed gaps in understanding, leaving open questions about the planet's hidden connections. For now, the only certainty was that the story was not yet finished, and the hazards, both known and unknown, remained under close watch. Right now, satellites still track the subtle pulse rippling through Earth's crust. As new rifts and tremors surface in unexpected places, the boundaries we thought were stable are shifting beneath our feet. Our planet isn't finished changing, and neither is our understanding. The next move belongs to the Earth itself. What would you do if the ground beneath you began to change forever? Share your thoughts below.